Hello, good people. Did you ever find yourself waiting for a date and to distract yourself from the thought that they might not show up, end up thinking about the nature of the universe and where all the atoms come from anyway? No? Well, maybe next time. For most intents and purposes, atoms on Earth are immutable and eternal. Outside of physicists playing with particle accelerators and ignoring radioactive decay, an atom on Earth will not become another atom. An atom of hydrogen will not spontaneously become an atom of helium. Recall that it is the number of protons that is responsible for the identities of atoms. There is no gentle way to increase the number of protons within a nucleus of an atom. Where did all of these different chemical elements come from? We need a bit of cosmology. Note that the values for time and percentages that I will be using here are not fully settled, and different sources may well employ different numbers. The first atoms to form were hydrogen and helium atoms, and they came to be a few minutes after the Big Bang, during the period known as the Big Bang nucleosynthesis. In those early moments of the universe, about 75% of all atoms were hydrogen atoms. The rest was helium. At this stage, these atoms were actually positively charged ions. They had no electrons. The universe was so hot that the electrons were too energetic to be captured into stable orbitals by the nuclei. It took another 500,000 years for the universe to cool enough so that the nuclei could capture the electrons and become the first true neutral atoms of hydrogen and helium. This was followed by a period known as the Universal Dark Age, a universe about as exciting as a nightclub on a Tuesday morning. There were no stars to speak of. Luckily for us, gravity pulled massive clouds of hydrogen gas together. At the core of these gas clouds, the pressure and temperature became intense enough for the process of fusion to take place. This led to the ignition of first stars. At the core of the stars, hydrogen atoms will fuse to give helium atoms. The byproduct of this is an immense release of energy that is responsible for heat and light. A lot of this energy is used to keep the fusion process going, and so it continues to give heavier elements. Depending on the type of a star, there is a limit to this, and it is reached with the element of iron, atomic number 26. Iron does not release energy when fused. In fact, we need to input energy to fuse it. So slowly, the energy available for the fusion process dwindles, and the stars can produce no new atoms. But how do we get elements that are heavier than iron then? Stars are engaged in a constant balancing act between two forces. There is gravity that is trying to collapse and crush the star, and then there is the outward radiation pressure of the fusion that is trying to explode the star. Once the star has used up its fuel and the fusion process slows down, the outward radiation pressure drops. Gravity starts to tip the balance in its favor. Eventually, the star collapses. It does so in a matter of seconds. This event is so violent that the shockwave causes the outer layer of the star to explode outward. This explosion is known as a supernova. The energy of a supernova provides the energy needed for more atoms to be synthesized. In fact, most of the iron is made during a supernova rather than at the core of a star. Furthermore, the explosion spreads these heavier elements into the universe so that they can be used in the creation of other stars and planets. However, even the explosion of the supernova is not energetic enough to get us past zirconium, atomic number 40. So that is still less than half of the elements in the periodic table. For the rest, we need to look at the remnant of a supernova. Depending on the size of the star that collapsed, we can end up with a black hole or a neutron star. Neutron stars, as you might suspect, are made mostly of densely packed neutrons. When neutron stars collide, they provide an abundance of free neutrons that the nuclei of other elements can capture, and so we end up with isotopes of various elements. Recall that isotopes are atoms that have the same number of protons, but a different number of neutrons. Without going too much into physics, under right conditions, a neutron can become a proton. It is transmuted. This means that we have changed the number of protons inside the nucleus, and thus the identity of the atom. Suddenly and dramatically, we have new, heavier atoms. Now I admit, I skipped a lot of detail here, but what I'm trying to get across is that the stars are the ultimate source of the elements in the universe. And so, as Carl Sagan, an American astronomer, said, we are all made of star stuff. Two really interesting things for the end. Even 14 billion years after the Big Bang, about 75% of observable matter in the universe is still hydrogen. Helium is responsible for some 23%, and all of the other elements combined account for the remaining 2%. Secondly, energy and matter are connected. We can explain the origin of the elements in the periodic table, but they only account for 5% of the energy content of the universe. What is the rest? Currently, we talk about dark matter and dark energy. They are called dark because they do not interact with light. But more importantly, they are called dark because we do not know what they actually are. The universe is a wonderfully strange place. It demands a heart of an adventurer and a soul of a poet. That is all for now, and I will see you on the flip side.